This is Lab 4, Oscillation of a Swinging Spring Mass System by Carter Yunt. The objective of this experiment is to observe the motion of a spring mass system oscillating in two dimensions by using conservation of energy, or saying delta E in the end is equal to 0. The system includes the mass hanging on the spring itself, and the Earth. Some conditions. We set the mass equal to 0.402 kilograms, which is from the 1D spring motion lecture video, a spring constant of 6.83 newtons per meter from the 1D spring motion lecture video. We set the time step equal to 1 over 210 seconds, or 0.0048 seconds, and said negative y-axis is down, positive y-axis is up, negative x-axis to the left, and positive x-axis to the right. So some physics concepts. So we're going to say that delta E here is equal to 0, delta E being equal to the change in work plus the change in thermal energy. Since the change in thermal energy in this situation is going to be equal to pretty much 0, we're going to say delta E is going to be equal to change in work, which is the change in work due to gravity, change in kinetic energy, and change in spring energy. We said that gravitational energy is equal to mgh, spring energy is 1/2 times k, the spring constant, times s squared, s being displacement, and then k is equal to 1/2 mv squared, mass times velocity squared. And said p at the period is equal to t, which is equal to 2 pi times the square root of the mass over the spring constant. So in order to analyze the data, I imported the video of Dr. Greco with the spring mass system and a tracker. I set the length part equal to 0.7 meters, and then use that to find the positions in the x and y direction. And this is the data that I got from the tracker. Now for the changes in my Python code, I set the ball mass equal to 0.402 kilograms, the ball position equal to the initial position that I obtained from tracker, and velocity equal to 0, and time equals 0. Then I read the x and y components from the CSV file I saved from tracker and set delta t equal to 1 over 210 seconds. I set the gravitational force constant at 9.8 meters per second squared, and the k value for the spring at 6.83 newtons per meter. The initial length that the spring is stretched from its relaxed position is 0.123 meters, and I said L is equal to ball position minus spring position, L hat equals L over mag of L, and the displacement then is mag of L minus L initial. To compute the energy systems then, I need to set the k equal to 1/2 times mass of the ball times magnitude of velocity squared, gravitational energy equal to mass of the ball times gravitational constant times ball position in the y direction, and the spring force equal to 1/2 times k times the displacement squared. Then I set a while loop, and I said while t is less than 9.307 seconds, which is the last time I had taken from tracker, I set initial k values, initial UG values, initial US values. So the force of gravity is equal to the vector of the negative ball mass times gravity, which acts only in the y direction, and the force of spring is negative ks times s times L hat, as defined before. F net then is going to be the force of the spring plus the force of gravity, and then the velocity of the ball is going to be equal to the initial velocity of the ball plus F net over mass of the ball times delta t, which can be obtained by setting F net over m equal to change in momentum, and said the ball position is equal to ball position initial plus velocity of the ball times delta t. Then I have to update the spring. I said L is equal to ball position minus the position of the spring, L hat equals L over mag L, and the displacement is mag L times L initial. The spring axis is then equal to L. Then to calculate energy changes, I set K, UG, and US equal to the ones defined before, and then said the change in them is equal to the new minus the initial. As you can see on tracker, this blue ball represents the position calculated in the Python code, and the red ball is going to be the position that is obtained from the CSV file saved from tracker. The difference can be set equal to external forces that were not accounted for, and as well as human error in tracking the spring position. So here's the graph from Python. I said delta E is yellow, which is the straight line. The gravitational energy is the green line. Kinetic energy is the blue line, and potential energy is the red line. My results that I obtained from the Python code, as you can see, delta K, delta US, and delta UG add up to delta E, which is very, very small, nearly 0. What does it mean? For your model system, is energy principle satisfied? Yes, it is. Delta E is equal to negative 1.49 times 10 to the negative 5th joules, which is pretty much 0. Small external forces acted on the system in the video, causing small changes. Also, human error can be, factored into that with the tracker video. For the second what does it mean question, I have to use the data you obtain in the tracker to make two separate estimates of the oscillation periods, one in the x direction, one in the y direction. Since the oscillation is in two directions, the equation t equals 2 pi square roots of m over k does not work in both directions, only in the y direction. To find it in the x direction, what I did was I imported the graph from tracker, and I found the point where it returned to its initial value, clicked on it, and found the time at that point, which came out to 1.61 seconds. I did the same in the y direction, which came out to 1.52 seconds. Thanks for watching.